Yes, it's Tim. You can start.
Okay. So hi everyone, I'm Shelby. I'm the president of Albertaloop. We are the Hyperloop group based out of the University of Alberta. And yeah, I'm gonna be going through our onboard electronics with you guys, or Alex is gonna be for the most part. Yeah, next slide. So yeah, here's just a render of our pod. You can see most of our sort of components. I'll be going through here our like team history and sort of progress in recent times. So yeah, design changes, team restructuring, and other challenges. So we're a fairly new team. We started recruiting team members in fall of 2019. And of course, due to COVID, a lot of our work overall has been remote. Which is definitely not quite as fun or satisfying as actually building things in real time as you design them. So it's been definitely tough for our team, but we've also learned how to kind of adapt to it and keep things going. And yeah, now that we're back, starting like this September, we've been ordering parts and building things. So we're kind of in that stage of our pod development right now. And yeah, our recruitment hasn't been great this year just due to COVID as well, you know, things getting in the way of in-person events. And then of course, another challenge with especially this specific subsystem of our cooling and controls is like microcontroller shortages and rising costs, just due to like global supply issues. For example, our accelerometer and gyroscope we need is out of stock everywhere. So just kind of challenges like that, I'm sure a lot of your teams can relate to. And then, yeah, just kind of going through our major design changes that we've had throughout our time as a club. So, of course, we initially had, you know, just initial planning for the SpaceX track based on the 2019 rulebook. And then the first change after that was the semi-final design for the SpaceX track. So again, all of this was done through COVID pretty much. So no actual physical prototyping really, or very limited. But in this iteration of our pod, we had an active and passive levitation system, liquid cooling, laser distance sensors, and a pressurized pod. Then the second design change after that, SpaceX was, it became apparent it wasn't going to be happening, and the CHC track was announced. So this is where we took away levitation and we added air cooling to the design. And then also third design sort of iteration, we did some team restructuring and brought back liquid cooling. And then fourth design sort of redo, the CHC pre-released, or you guys did the pre-release of your rule book. So we adjusted to the 250 kilogram weight limit and just other stuff like that. We also scrapped liquid cooling again. And yeah, we considered adding heating for batteries and other systems in the case that we're having to test either at the CHC or at home during the winter. And yeah, we added a GPS module. And then for the final one, just very recently, we discovered that our limb was too heavy for the CHC weight limit. So we've redesigned it to be just kind of smaller and scaled down. And so this means some changes for pretty much all of our systems to adjust to that. And yeah, that's kind of it. Now I will pass the mic over to our cooling and controls team lead, Alex. He's going to go through more in depth what our cooling and controls looks like.
All right. Before that, just the current development phase that we're on. So we're still currently in the design phase of things, but switching over to early prototyping. All of the pod circuitry is dependent on the elements that they control or communicate with, and with so many design revisions, there have also been a lot of changes on the controller side as well. So currently, some circuits have been prototyped like on breadboards, but a lot of them are still virtual or still concept sketches. Most of the sensor types that we need have been purchased, but the remaining quantities will be when we actually finalize the PCB designs. And for these prototype circuits, we're mainly using the pre-built breakout boards that we could find with the sensors on them until we can manufacture our own, and this basically just speeds up development time. All right, so the electrical system summary. This is just a rough layout of a potential layout of what our onboard PCB enclosure might look like. So In case of malfunctions or part failures, which is to be expected at some point with prototypes such as these, it's important that all important components, such as the microcontrollers or sensors, can be swapped out very easily, which basically means that they're either connected by a wire that's removable, or they sit on top of the PCB as mezzanine cards connected via pins and sockets. This makes it easier to swap out components and cheaper as well, versus like actually having to go and fully replace a PCB with everything on it. You can just swap out a couple things on top, and that also helps to minimize turnaround time. Some sensors are also in banks, which are grouped together and potentially toggleable with inline dip switches, which basically just enable and disable the chip select pin, and the software compensates for them. We also have our high power noise isolated away from the low power system as much as possible using filtering and like physical separations in the power lines. And most PCBs will be located within a metal PCB enclosure, which helps to reduce the radio frequency interference effect that is produced by some of the larger components. It also helps with accessibility of them. So the low power system. The system itself is in the early stages of development, but we have a basic idea of what we need from it, which includes 3 levels of low voltage DC power, 5 voltage going to the microcontrollers and sensors, 12 volts for fans, relays, and contactors, and 24 volts almost exclusively for solenoids that are around the pneumatic braking system. And then we have the higher power system, which is a bit more developed, but we're still thinking a couple things over. So going through the system map here, we have the high power batteries, which are monitored by the BMS, both current-wise and temperature-wise, and all of those batteries and get basically grouped together as on the power junction board, which is connected to the main backbone wire. And then there's a bunch of current sensing that goes on there, which also gets reported to the BMS. Then we have the high power contactors, as well as the safety circuits and pre-charge circuits before they all connect into the Bamilcar D3, which is our variable frequency drive and power inverter. That converts the DC power into 3-phase AC, which also gets split again from that one Bamilcar to both linear induction motors. And then they're grouped back together at the end as a Y connection, which should theoretically ground them, but in case we have a neutral wire heading back to the Bamilcar as well. And there's also a bit of cooling attached to those high voltage wires. Okay, the onboard interface PCB. This is a general layout of it. You can see 2 parts to it. On the far left is a bunch of mechanical or manual toggle switches with LEDs around them, and on the right is the actual control interface, including the e-stop switch. So the manual switches are for controlling the contactors, both high and low power. Of course, they don't control them directly because a pre-charge circuit is also needed. So instead, the signal, if they're switched on, goes back to a logical AND gate, which compares the logic through that as well as what a microcontroller is outputting, and that way we can shut it off manually or automatically as quick as possible. On the interface side, there's a 7-inch LED touchscreen to display sensor data and error codes, and also configure settings. And that interfaces with the Raspberry Pi 4B, and some other buttons and switches also interface with that, including an e-stop. It also has a piezo speaker that can relay beep codes to us in case of failures, especially if we can't like get close to the pod if something is dangerous. Okay, contactor control PCB. So this is basically what those mechanical switches connect to. There's some connectors here to LEDs and the switch as well. The contactor control PCB consists of this is a bit of an older version. So instead of a DB9 port, there's a RJ45 or RJ47 port here for a canvas line, which goes to a canvas transceiver, which ties into our microcontrollers. On the pod, we're mainly using TNC 3.6 microcontrollers. And then, as mentioned before, the actual contactor itself is a mezzanine card, which just plugs into this PCB. Or, sorry, the relay to control this contactor is on the mezzanine card. And all of the microcontrollers on the pod communicate with each other via CAN bus. You can see one of the prototype circuits here from one breadboard to the other. One TC is connected up to an accelerometer and gyroscope. When that senses something, it would have sent a signal over the CAN bus line. In this case, it's just using a twisted pair of Ethernet to another one, which would activate an LED. Of course, with CAN bus or a controller area network, each node is connected to a central bus, and that means that each of them can communicate with each other. For the actual cable, we're thinking of using Ethernet just due to their availability, and also being twisted pairs helps to reduce interference. All TNCs receive the messages sent along the line. The software decides what to pay attention to. You can see a map of all of the connections on the bottom. There's about 6 to 8 different types of subsystems. Some of them might have multiple PCBs depending on their placement around the pod. Okay, and now we have the air cooling system, which is our primary cooling system on the pod. By using 4-wire fans, we can easily adjust the volumetric flow rate values or the fan speeds, just simply by modifying the signal sent over the TNC's power pin. And when used in conjunction with temperature sensors, we can make this the power usage much more efficient. These fans can be networked to function either individually or in arrays, depending on if their signal pins are wired parallel. And on the pod, there are 2 somewhat separated air cooling systems. One of them is for the PCB enclosure, which is more shielded and filtered, and the other one is a larger ducting system for some of our higher power or larger systems, such as the linear induction motor or power inverter. Multiple types of fans were purchased and were tested in different configurations, as well as different filter values, and the most suitable ones were identified for each system. The brake controller PCB. This is what you see right here is a SolidWorks model of our braking system. It's fully pneumatic and controlled by solenoids. So this one is in the very early stages of being prototyped. Basically, the solenoid valves use relay to actually activate them. And of course, the TNC 3.6 can only output a maximum of 3.3 volts per pin. So we need the relay to switch the voltage to the 24 volt need for the solenoids. And they work in tandem with the pressure transducers on the line to perform braking operations, as well as different safety checks for pressure and valve positions.
1 minute left.
Temperature sensor PCB is basically grouping a bunch of different temperature sensors together. This has the toggleability also here. I'll just try to go through this a bit faster. So they're located in different parts of the aeroshell, and they're rated based off of their of what they have to sense the temperature of. The LED state indicator, of course, is going to be controlled by BJTs as well as relays for power. And these basically use individually addressable LED light strips to tell the pod state. And then we have a couple other types of PCBs here, including the CAN bus signal translation module, which just translates the signal from the BAML card to the rest of the CAN bus line. The navigation module has an accelerometer gyroscope, and that communicates with the onboard computer. And the GPS module works with it in order to actually locate the pod in space, and just as another reference to our location acceleration. The main onboard computer is another TNC running state machine, and it connects to Raspberry Pi, which acts as gateway module for security, and also connects to the radio for communications. And this is the GPS module board. Okay, are there any questions? And thank you for listening to our presentation.
Thank you very much for your presentation and introduction to your system, Albertaloop. And I'm looking forward to hear some questions now on that, since we will enter the Q&A session. So how this works is you can either type a question in the chat or simply raise your hand and I will call you out. Are there any specific questions currently? Okay, I would actually have a question regarding your CAN bus. Is there like a specific protocol you're planning to use, or like an architecture? Or is it like bare bones CAN messages?
Probably not the right person to ask for this. This is more software related, but there is like a basic CAN message structure that we're going to be using for the messages. I can't remember which protocol exactly it is.
Okay. Okay, since there seems to be no question as of now, I would say thanks again for your presentation. And I basically wrap this round, and we will continue in 9 minutes with the next presentation.